All right, today, first day of our unit on light, we're going to talk about the electromagnetic spectrum. And I'm taking notes in a notebook. I'm doing Cornell notes. I recommend that you do the same, even though there's no way that I'm going to be collecting and grading these. It's just going to really keep you on track. So I recommend getting out something to write with and getting some paper in front of you. I'll show you my notes at the end of this so you kind of see what I wrote down. First thing you need to understand about light is that it's a wave, just like we've been talking about. It's a transverse wave. That's the kind of wave that goes up and down as it's traveling. Um, it travels through empty space, which means it doesn't need a medium. It's not like sound that needs to travel on air or water or some other type of matter. Light can travel through absolutely nothing. The part of the electromagnetic spectrum, which is a new term that we always talk about, is the part right here, this tiny little sliver in here where the entire rainbow fits. This little part of the electromagnetic spectrum is all that human beings are able to see. And it turns out that that's within a range from 700 nanometers, we'll talk about what a nanometer is later, to 400 nanometers. Those are the wavelengths of light that the human eye is capable of seeing. Okay, so we said light is the visible part. When we say light, that's what we're talking about. But there's this other entire electromagnetic spectrum with different sized waves that we're just unable to see. So when we talk about light, we're really just referring to the part that we're able to actually see. We talked about how that goes from the color red to the color violet. Notice violet has the smallest wavelength, red has the longest wavelength. Whether you're talking about violet or red or radio waves or gamma rays, whatever type of light that you're talking about, whatever type of electromagnetic wave that you're talking about, they all travel at the same speed, which is this number right here. It's the speed of light, 300 million meters per second. That's a lot of zeros, so you usually see it written in scientific notation like this, 3 times 10 to the 8th meters per second. In miles per second, that's 186,000 miles every second, which means that if you turn on a light, that light is fast enough to go all the way around the world over 7 times in 1 second. So this is a really, really big number. It is the fastest that anything in the entire universe can travel. It's like the universe's speed limit. Just to get our math straight, there's really nothing new from this unit so far. We know that from our previous unit, the speed of a wave, which is v, is equal to the frequency times the wavelength. We also know from all year long that speed in general is just distance divided by time. So that's nothing new. The only thing that's new now is we're talking about a very specific speed. Just like we talked about with sound. Sound travels at 343 meters per second. Same thing here, except light is just way faster. So if you want to find the frequency, you start with this equation here. To get the f by itself, you got to divide both sides by the wavelength, that's lambda. On the right, it cancels out. If you rewrite it, frequency equals speed divided by wavelength. Again, we've done this before. Again, reminding you, frequency has units of hertz. Wavelength is basically the same process, except now you're trying to get lambda by itself instead of f. So you're going to divide by the f. The f will cancel off, and if you rewrite it, wavelength is just speed divided by frequency. Units for wavelength are meters, and again, back here, units for speed are meters per second. You might want to pause it here and just copy this table down. Those are the three equations, four if you count this one, that you're going to need for most of the math in this unit. Okay, starting with what you know about light, everybody's pretty familiar with the colors of the rainbow. You now know that red has the longest wavelength, turns out to be about 700 nanometers. As you go from red, orange, yellow, green, blue, indigo, violet, you get smaller and smaller in wavelength. What that means, because the wavelength is smaller, but they all travel at the same speed, as your wavelength gets smaller, your frequency gets bigger. So red is the longest waves, but the smallest frequency, and therefore the smallest energy. Violet, or purple, has the shortest wavelength, which means it has the highest frequency, and that turns out to give it the highest energy. And this isn't just true for colors, this is true for other types of electromagnetic radiation, like we'll talk about in just a minute. So this tiny little part right here, that's everything you've ever seen. Anything that you've ever seen with your eyes has been due to some light in this little range right here bouncing off of it. But look at everything else that's there that we are not able to see. This entire spectrum is called the electromagnetic spectrum. And just like red goes from long to short as you go across to purple or violet, radio waves are the longest type of electromagnetic radiation. And then microwaves, and then infrared. Infra means below, so it's just below red or before red. Then you got Roy G. Biv, and then you have ultraviolet, meaning just higher in frequency than violet, and then X-ray, and then gamma ray. Now I'll zoom in on a couple of these, give you a little more detail. So radio waves, they go on the far left end. They are important to know because they're the biggest. Because they're the biggest, they have the lowest frequency. That means they have the lowest energy, which also means that they're relatively the safest for human beings. Microwaves are just shorter than radio waves. Microwaves as in the type of waves you use to cook your food in a microwave, but also they are used for some other things like signals in remote controls to turn on your TV and some other applications as well. That brings us to infrared. And this is another name for heat, body heat, like when you use night vision goggles. Those goggles are picking up on body heat. The scientific name for heat is just infrared. Then you've got the colors you know. That's visible light. Just past violet, just higher in frequency is what we call ultraviolet. These cause sunburn. Past ultraviolet, you have X-rays. And then at the highest end of the frequency, but the lowest end of the wavelength, you have gamma rays. Somewhere here from ultraviolet to the end, you have radiation or light that is called ionizing radiation. That means it's a little dangerous for us, so it can do some harmful things to the human body. Okay, there's one more look at the entire electromagnetic spectrum. And again, the point is this tiny little part right here is what we are talking about when we say light, but there's a whole lot of other wavelengths that we just aren't able to see. Some of the uses for some of these other wavelengths and applications. So one thing that we know is that even now, as I'm talking, as you're listening, there is electromagnetic radiation going through the room that you are sitting in. If there was none, the room would be completely black. But beyond the colors that we can see, there's X-rays and microwaves and radio waves traveling through space all the time. So it's constantly in the space surrounding us. The reason that they are called electromagnetic waves is because light, as we know it, is made up of two fields, an electric field and a magnetic field, and they kind of travel together, as shown in this picture. So that's where the phrase electromagnetic comes from. Just one specific example of light here, because light travels as two different alternating transverse waves, sunglasses that have a polarizing filter are able to block out a fraction of that light and make it appear darker. Here are some examples of practical uses of other types of radiation. Radio waves, we send information with that. Literally radios use them, but also television and other types of broadcasting. Microwaves, you cook food with it, and you can also send messages in the microwave range. Infrared is heat. Anything that you use heat for, you are using infrared. Visible light, couldn't see without it. Ultraviolet is good for us up to a point, but too much can be harmful, causing sunburn or even cancer. X-rays, everybody is probably familiar with an X-ray being used to take pictures of the harder part of your body, the bones inside your body, and it travels right through soft tissue. So it's very, very useful in the medical world. And gamma rays, there's all kinds of uses for gamma rays, but they are also very, very dangerous. So they, you don't want to be exposed to gamma rays at too high of a concentration. Okay, to light. Light as we use it on a daily basis. Here's 3 pictures of light bulbs. I'm going to go through these one by one, and we are almost done with this video. This is the original type of light bulb that was first invented by Thomas Edison. And it's basically an empty tube that has a wire running through it. And when you run electricity through the wire, that wire glows. When a wire glows, if you run electricity through it, that's called candes or incandescent light bulbs. So now, rather than just having a vacuum inside the tube, it's been discovered that having inert gases like nitrogen or argon inside can help the glow, help the light to work properly. But these are considered kind of old technology. We don't use these as commonly anymore. The next version of light bulbs that you probably have seen are fluorescents. And fluorescents are basically hollow tubes that are filled with gas that gets excited by a voltage. And when it gets excited, those gases release light. So this is more efficient than the original light bulb, but has been replaced since by something called an LED, which I'm sure many of you are familiar with. LED stands for light emitting diode, and it's the most efficient way to produce light because every single electron that flows through an LED releases one photon of light. So they use very little electricity and they can produce very, very bright light. That's it for our video. There's some other applications that I'm going to show you here in a little bit more detail later on, but signals being sent from radio stations and television stations, basically they can change the frequency of the electromagnetic radiation, and that's what gives you your different channels. The government has posted ranges that are acceptable to broadcast in, and these are some of the common ranges for AM radio right here. Very high frequency is what VHF stands for. That's right here. FM radio is in this range right here. And then ultra high frequency television is at the high end of this. Now, if you notice, KHZ, that's kilohertz. MHZ, that's megahertz. Kilohertz is in the thousands. Megahertz is in the millions. So all that's different about all these different signals is their wavelength and their frequency. That is it for this video.